Welcome to Unfold Data Science. My name is Aman and I am a data scientist. In this video, I am going to explain you what are large language models and how it works. Please take out a notepad and a pen and please be with me till end of this video, and I promise you are going to gain lot of knowledge in this video. Let's dive in. Let's try understanding about large language models by breaking it into piece by piece. So first component we are going to pay attention to is basics. So some basic terminology, some basic concepts which will make the solid foundation for you to understand the complex concepts. Then I'm going to talk a bit about development of LLMs over the years. Fine. After that, I'm going to do a Python hands-on exercise in front of you and try to explain you how LLMs work internally. So through this assignment, you will get a very good intuition of how things are working internally. So this is the most important part of this video. And after that, I am going to give you some learning materials for the next lecture in this series so that you will be prepared to digest the upcoming concepts in this series. So people who are new to this series, this is a new playlist or series started at Unfold Data Science. The name is LLM for Application Development. And my intention in this series is anybody who learns from here should be able to build and deploy LLM applications right from understanding all the concepts till building applications and deploying it for the production ready use cases. So in the first video of this series, we covered about generative AI. If you have not watched, you can watch that. This video is about large language models. So let me write here large language large language model. The reason I'm writing it here is it is very important for us to break it and understand what it means. So I can break it into two parts. First part, I will call it large. You can think this as a separate part, and language model, you can think as a separate part. First of all, let me try to tell you what is the meaning of a language model. So if somebody asks you what is a language model, you can very simply give an answer and keep it very simple. Say that a type of AI that designed to understand and generate human-like languages. So what is a language model? It's basically a type of AI to understand and generate. Please pay attention to these keywords here. Understand and generate human-like human-like language. Fine. So this is a language model. Now, what can be some of the use cases of this language model? So, for example, if I write here a word called I love blank. Suppose my language model is trained on similar kind of data, then my language model can fill this blank by saying I love pizza or I love dogs. How it works, I had briefly touched into the last lecture. So basically, all the candidate words will have a probability of occurring here. So in this case, let's say the probability of pizza occurring there is 0.8, probability of dogs occurring there is 0.2. Since the probability of pizza is higher, so pizza will come and sit here. So this happens after your language model has been trained. But for training your model, you need some data, right? You need some data. So we will discuss that. But what can be some of the key characteristics of language models? So please just note here if you are noting. Key characteristics of language model is these are deep learning based model. So as I told you in machine learning and deep learning and advanced AI, right? There are various approaches to do things. Deep learning is one of the approach. So language models is basically a deep learning based models. What are the second characteristics of language models? Language model work on massive data set. So I told you it is trained on massive data sets. So it is deep learning based. It is trained on massive data sets, and most of the language models are transformer architecture. So please make a note of this. Most of the language models are in some way or other transformer architecture. So from here on, whatever I'm going to explain you, that will be one step in learning transformers. Any topic that I touch upon, take it as this is one step in learning transformers. Fine. So this is a very, very important concept that you should know. Then only you will be able to understand language models properly. But before that, as I told you, we will cover basics first. What are the capabilities of large language models? So to understand the capabilities, right, we can simply go to any of the language model, for example, Gemini or ChatGPT, and we can do a lot of things. What is the use? Let me write properly. So it can do a lot of things, right? I'm not going to spend a lot of time here. What is the use of language in, I'm asking a basic simple question, human history. So it can give us a answer. It can draft email for us and many things. You already know all these things, so I'll not put a lot of time. But one important thing that you need to understand is these language models are deep learning. It consumes massive data set and most of it are transformer architecture. This is about this part, language model part. But my interesting part here is this part, that is large. My question to you is, what is large in large language model? This is my simple question to you. You can pause this video and tell me what is large in large language models. Okay. So now what I'm going to do is I'm going to explain this concept from a recent development. As I'm shooting this video, it has not been 24 hours since a news has come in the market. And the news is Llama 4 has been released by Meta. Okay, so if you do not know, Meta is basically Facebook company. Llama 4 is their family of models which they release. And if you go to Google and search for, Llama 4, right, you will see that there is a lot of news on Llama 4. So see here, 7 hours ago, Llama 4, 15 hours ago, Llama 4, 1 day ago, Meta releases Llama 4, a new crop of flagship AI models. So to keep it simple, a new beginning, that is Meta is claiming, this is Meta's page. The Llama 4 heard the beginning of a new era of natively multimodal AI innovation. So which means that a new version of Llama model has come into the market. Why I opened this page is I want to make you understand what is meant by, or what are the key characteristics of model and what makes language model as large. So if you see here carefully, guys, these are different variants of model. Here, pay attention, 288 B active parameters. So you see this B here, okay? B stands for billions. So what makes large language models large is first parameters. Okay, so we will go to our note and we will keep writing here. So first of all, what makes what makes LLM large? And the first thing that makes LLM large is called parameters. We will understand what is this, don't worry. And if you go to Llama page again, you will see one more thing here. Native multimodal with 1 million context length. 1 million context length. Here you see industry leading 10 million context length optimized inference. So second thing is context length. Context length. And third thing is if you go and do a control F and you do token, right? You will see this word is mentioned so many times here. So it is saying Llama 4 enables 1 billion token each, etc. And I'm interested in this line particularly. The overall data mixture for training consists of more than 30 trillion tokens. The meaning of this is the model is trained on 30 trillion tokens. So what is the third thing that makes your language model, large language models large is tokens. Fine. You will understand how large language models work if you understand these three concepts carefully. And of course, there are many things which we will cover, but these are the basics that you should understand first. Let's go ahead and try to understand the first concept, that is known as tokens. So I will pick the simple ones first, and then we will go to the complicated ones. Tokens. You remember I wrote a word called I wrote a sentence called I love pizza, right? When a language model processes these sentences, right? When a language model processes these sentences, how it looks at it is basically some individual identifier. So, what I mean to say here is the token is most basic unit of data in a language model. So, if somebody asks you a formal definition, right? Most basic unit of data in LLM. So if Meta is claiming that I have trained my new model on 30 trillion tokens, then you can think of 30 trillion most basic unit of data. Now, you should not think that token means one word. So you should not think that I will be one token, love will be one token, and pizza will be one token. It can happen, but there are more details around that. To give you a solid understanding of what is tokens, let me show you something. So I will go here and I will open, let me try opening a very nice app that is known as Tick Tokenizer. Okay. In this Tick Tokenizer, right, I will go and choose a simple model first. And what you can do here is you can write something here. For example, I love pizza. So if you see here, it will tell you how many tokens this particular model is treating this sentence into. For example, if I take my cursor on I, you will say 40 is getting highlighted, which means the word I will be identified by the model using this number 40. The word love will be identified by the model using number 3021. But in pizza, you see there are three different tokens created. So space P, that is 281, IZ, that is 450, double A, that is 5418. So what I'm trying to, sorry, I've written wrong spelling of pizza here probably, but anyway, let me write like this. So three tokens only, fine. So that also gave you an idea of how it will vary if misspelling and these things happen. Okay. So here, three tokens for three words, which is fine. Now I will write a different sentence here. For example, I am a data scientist and I am a data scientist and I love data science. So what I want you to pay attention here is the word I is token number 40 and the word data here, right? Data here is token number 828. So next time when I write data, it should get identified with the number 828 only. So if you see here, next time data is getting identified by 828. Fine. And if I write something which is little misspelling, for example, KYTBS, I don't know. So you see here, this is not a common English word, so it is trying to break it and try to understand what is the meaning hidden in it. But the message I want to give you from this exercise is tokens are the basic units of data that language model processes. Can token be words? Yes, it can be words, but most of the time it's not words, it's pieces of words. Okay, so here scientist is a word, but this word, right, this is a piece of the word. So in terms of word count, I'm having these many counts. In terms of token counts, I'm having these many counts. But if I go back to my simple example of I love pizza, in this case you can see I have three tokens because model identifies those words. Those are common words. And if I go to a different model, right, then you will see that the way it produces tokens is different. For example, if I change it to GPT 3.5 turbo, right? So you are a helpful assistant. Now let me write here, I love pizza. So please pay attention here. There is a special token here called IM start. IM start means message start. That token is getting identified by 100264 number. Then system message will come. So system is identified by 9125. And then you are a helpful assistant is there. Then IM ends. IM ends means that messaging, one message ends. Okay. Then IM start. One more time IM start. And if you pay attention, right, IM start 100264 here and here are same because both are message start. Then user comes. Then I love pizza. 3 tokens for I love pizza. Then IM end. 1 token. Then IM start. Then assistant. So what I'm trying to tell you is you can think of when you process a language, right? Through these numbers, language model will understand what is coming to me. Okay? Keep it very simple. Language model will understand what is coming to me through these numbers. And if I go to my note and if I write here, for example, I love pizza. And let's say the token for this, token means you can think as an identifier. Identifier for this is 1, for this is 2, and for this is 3. So this is token number 1, that is token number 2, and token number 3. What you have to tell me is you have to pause this video now and you have to tell me what is the problem, what is the problem if I process my input like this. What is the problem if I process my input like this? So I have come across a nice tool called Excel I draw, and here I will paste a sample, whatever question I'm asking you. So here, what I'm saying is the tokens have been created. My question to you is, if I do training using these numbers, then what is the problem? I'm sure some of you would have right answer for this because this is not something that is very, very complicated to understand. So basically the thing is model training is internally a mathematical equation. Okay. And in the mathematical equation, if you are giving word number 1 more priority than word number 2 or vice versa, that's not a right thing to do. So imagine a mathematical computation going on. In that mathematical computation, you are giving love word higher number than I word, pizza word higher number than love word. That's not a right thing to do because in mathematics, if you multiply something by 3, that becomes 3 times. If you multiply by 2, that becomes 2 times. And you already saw the token can be any number. For example, one token is 882, other token is some other number, right? So in a mathematical equation, if you put tokens as a number, that's not a very good idea. So we cannot process text using tokens. We cannot process text using tokens. Remember this. Okay, I will write here. We can't process text using numbers. Tokens, sorry, using tokens. So we cannot do that. What is the way out? What initially I'm telling about, not very recently, but as I told you, I will give you some history of how the things have evolved, right? So what people did is they used some very basic and native concepts. Okay, and those native concepts are, let me explain you in Notepad. So what they thought is, if there is a sentence called I love pizza, fine, and if there is a sentence called I love dogs, fine, what we will do is to represent this in a better format, what we will do is we will create a table like this where we will say all the individual words in this data. I love pizza and dogs. And this is my sentence 1, right? So I word is present in sentence 1. So I will write here 1. Love word is present in sentence. So I'll write here 1. Pizza word is present. So I'll write here 1. Dogs is not present. So I'll write here 0. For the second sentence, what I will do is I will come here and I will say I word is present here. So 1. Love word is present here. So 1. Pizza is not present. 0. And this is not present. Dogs is present. So 1. So what they thought is this will be representation of my first sentence and this will be representation of my second sentence. And when I'm saying these words, right, you should always think tokens. So I may be token number 24, love may be token number 42, just some random numbers I'm giving. This may be 201, this may be, let's say, 106, some random numbers I'm giving. So this approach of presenting the text into numerical format, right? Machines can process numbers only, it cannot process text. So we need to put it in number format. And there are two approaches here commonly known as, one of that is known as bag of words standing for BOW, and another is known, I mean related one only, one hot encoding. So what we do here is, for example, here, let's say pizza word is present 2 times in first sentence. So what people thought is we will make this one as 2 also because it is present 2 times. Okay, these are very old techniques. I'm just trying to give you some understanding. So what could happen is, through this approach is, you can represent a sentence or a document in a large vector, and you can represent individual words also into vectors. For example, the word I can be represented as a vector 1, 0, 0, 0. Why? Because I is word number 24. Similarly, the word love, which is word number 42, let's say word number 42, that can be represented like 0, 1, 0, 0. Similarly, the word pizza, which is word number, let's say 201, can be represented as 0, 0, 1, 0. And we call these very initial word vectors. So what are these called? These are called word vectors. But again, I want you to pause the video and try to tell me what is the problem with this approach. So here what we are doing is we are simply counting, or we are seeing which word is present, which is not present. I'll give you some context by giving a simple example. So imagine there is a word called, there is a sentence called, I love pizza and I know it's unhealthy, still I love it. So something like this. Something like this. So if you see here, right? I love pizza. I know it's not healthy. However, I love it. Basic one hot encoding. So it will take all your unique tokens. So whenever I write tokens here, this is just for understanding purpose. You should always think these as numbers. For example, healthy is number 44. Just an example. Word number I can be represented like this. Word number its can be represented like this, and so on and so forth. And if you put it like this, right, then it is called as a word vector. So in all these approaches, what we are trying to do is we are trying to create a numerical representation of these words. We can feed these words into the training and we can try to build the model. But my question to you remains same. What is the problem if I do my training like this? So initially people have done training like this, but what is the problem here? The problem here is system is not able to understand any meaning. It is simply counting. No semantic meaning it is able to capture. Okay. No semantic meaning it is able to capture. So basically it is simply going and counting and seeing what is present and what is not present. It doesn't care what comes before, what comes after, what comes before, what comes after. Fine. So in that way, meaning of the words are not getting captured. So this is a problem. This is very basic, old technique known as one-hot encoding, bag of words, etc. After this, what happened is there came a concept of something known as word embeddings. Okay, and the reason I'm explaining you is I explained you tokens. Now I'm explaining you parameters. So if you understand these concepts, then it will be easy for you to understand parameters of a model. So what is the meaning of embedding? What happened is around 2013, right? Around 2013, a new concept came, new kinds of models came that told that, you know what, we have some idea where we will go and understand the meaning of the word. So what comes before and what comes after. For example, suppose there is a word called cricket and there is a word called mango. Fine. So there is a high possibility that cricket may come together with the word play or played or playing, etc. And mango may come together with the word eat, eating, eaten, all these things. So what researchers told that let's go ahead and build a model which can which can present a word in such a way that it captures some meaning of the word. So what you can think of is you can think of there is a word called cricket and there is a word called mango. Imagine that there are two axes. Okay, two axes. One axis is called eat and another axis is called play. Fine. One axis is called eat, another axis is called play. In the eat axis, cricket will have score of 0.1. In the play axis, cricket will have score of 0.9. Mango will have in the eat axis score of 0.8 and mango will have in the play axis score of 0.2. So the word cricket can be represented in a vector 0.1, 0.2. The word mango can be represented in a vector 0.8, 0.2. This is better than the previous approach because here it will be always 0101 one hot encoding. Maybe we can take a count. So no meaning is getting captured. Here at least some meaning is getting captured. Okay. And what researchers have done is they trained models and they plotted the words in a 2D plane. So what they did is they plotted the words. So suppose there is a two-dimensional vector and one dimensional is eat and another dimension is play. So what they found is when they trained the model and when they build these embeddings, right? These are called word embeddings. Then words like mango, okay, banana started coming more towards this side, and words like cricket, chess, these things started coming together. So this was a huge advancement in the field back in 2013 around that time. And there are some models which are doing these. One such model which I'm going to show you demo also now, it's called what to wake model. What this model does is this model will generate embeddings of your given words. So for example, if I give it a word cricket, it will give me this embedding. If I give it a word mango, it will give me this embedding. So this was a huge development from that age point of view, not current point of view. But there is a huge drawback of this approach. And the drawback of this approach is it will always generate static embeddings. Please understand this word very carefully. The drawback of this approach is it will always generate static embedding. What is the meaning of static embedding? The meaning of static embedding is I want you to pay attention to. I will write here two sentences here, and please pay attention to these two sentences. I was walking I was walking on the bank of river. This is one sentence. Another sentence is I went to the bank. I went to the bank to withdraw money. To withdraw money. Please pay attention to the highlighted word here. Please pay attention to the highlighted word here. And since you are a human, you have intelligence, so you understand the context in which this word is used here and this word is used here. But if you pass these two sentences through a word-to-way kind of model or static embedding model, it will give you same embedding for both the bank, and that is the problem. Okay, so the problem with word-to-way is static embedding. What we need is we need the embeddings to change based on the context. So here I want a embedding which can tell me that this is used in context of river and this is used in context of financial institution. That is the problem with static embedding. So let me try to put it here so that I can share this with you, and you can understand the concepts easily. So if I take these two sentences, right? If I take cricket, mango, eat, play, right? And if I pass it through a old embedding technique, what it will generate is static embeddings are not good for learning. So model will not be able to learn what is the context hidden. Fine. So three things you have seen till now in terms of development. So what is the definition of tokens? How initially embeddings were done using these tokens, how people came to some kind of meaningful embeddings, but these are static embeddings. And now as we move forward, we do dynamic embeddings. We are going to use an LLM and try to see the tokens and embeddings. First of all, let's try to go to Hugging Face. And if you do not know what is Hugging Face is basically an AI community where you get all these models. So models are here, model repository basically, and I can use these models from here. So for example, Quen 2.5 Omni 7B is one model here. If I want to use this, if this is an open source model, I want to use it, I can simply copy this address and use in my local. Okay. So what I'm going to do is I'm going to import one such model and show you how it is tokenizing and how it is generating the embedding. So let me try to import a Microsoft model. So that model is basically known as Phi3 model. So if you see here from transformers, that is transformer package, I'm importing auto model for causal LLM. That is basically one package you need to import for importing pre-trained models. Okay. And auto tokenizer is the module I'm importing because I need to show you the tokenization. And the model I'm using is this model, Microsoft Phi3 Mini 4K Instruct. So here, as I told you, right, every model will have an address. So this is the model, Microsoft model I'm using in my example here. And once this model gets imported, right, what it will import is the tokenizer. So if you see here, right, auto tokenizer dot from pre-trained. So I'm asking the tokenizer component of this model. Fine. So in the tokenizer component, what I can go is I can create tokens for my input sentences. Let me do that. So let's take our input sentence that we have been playing around with. And let's say tokenizer.encode I love pizza. So if I do this right, you will see that model is encoding it into four tokens. Okay. And if I have to see, if I have to convert it back to the original thing, right? What I can do is I can say tokenizer.decode, copy this and paste this. So what I expect is I love pizza will get recreated. Very simple but very important concept. Words enter into the LLM not like words but like these numbers. That is your tokenizer. Now, as I told you, previous ways of word embedding was static embedding, but new ways of word embedding are dynamic embedding. So let me show you how dynamic embedding works. And for that, I will use another model from again the transformer module, and I'll write some code here, but don't worry much about all the details of it. Basically, what I'm doing here is again from transformer, I'm importing a BERT model. Okay, I'm defining a function generate word embeddings. Fine. And here, if you see the same code, tokenizer is equal to auto tokenizer pre-trained model name. So my model name is BERT base uncased in this case, uncased. So if I go and search here, right? So you will see that Google BERT based, this model is my model basically. Okay. So that model I'm using, and that model I'll take from model name. Then I'm creating the tokens. If you see here, I'm creating the tokens. From these tokens, what I want to do is I want to create some word embedding just to show you that how it will create dynamic word embeddings. Here I am extracting embeddings from the corresponding words. I'll give you this notebook. Don't worry about the codes. Okay. Create a dictionary of word embeddings. I'm leaving some words. So as I told you, right? CLS, SCP, PAD, these are the tokens that is related to this model only. If you remember, right? When I was showing you tick tokenizer app, if you remember when I was showing you tick tokenizer app, I told you this IM start, IM end. Okay. These are tokens specific to this particular model 3.5 turbo. So in my case, right, these are tokens specific to that model that I'm using. So I'm kind of ignoring that. And I want to just see the original embeddings. So once that happens, right, what I will do is I will generate embedding for bank word 2 times for those two sentences. So let's go here, and I have created a function here. Okay, so I'll call this function with my text, and I will show you how bank words embedding changes. So text one is I was walking on the bank of the river. Text two is I went to the bank to withdraw money. First time let us import for text one. Okay, embeddings is equal to generate word embedding text one. So basically for all the words I am generating, I can generate for one word also. For all the words I am generating, and it will give me the embedding for all the words. So for example, bank word embedding is this. Okay, remember this is the bank word embedding for text one, which means in the river context. Now if I change it to text two, right, you will see that it will generate a different embedding for the bank word, right? Now the embedding is changed. This concept is called dynamic embedding. Dynamic embedding meaning the model is understanding that bank is used in a different context in both these sentences. So you understood two important concepts till now: the embedding, the tokenizers. Let me try to show you how these things build the parameters of the model. So going back to our example of predicting the next word, let's say this is the sentence we have been discussing. I love fill in the blanks. And we told that we want to put the word here which has the highest probability based on the model's training. So let's call this I as word number 22. And let's call this love as word number 34. So what we have learned till now is word number 22 will have its own word embedding. So let's call this is the word embedding of word number 22. And this is the word embedding of word number 34. And in embedding, we should put some numbers here, right? So I will call here, for example, A1, A2. A simple example I'm putting. And here I will put here A3, A4. Fine. Now, can I say that I can put these in a matrix? So in a matrix where A1, A2, A3, A4. Think like all the rows of this metric is one word. So this metric represents the word number 22, this row, and this row represents the word number 34. Imagine there is one more matrix. Imagine there is one more matrix. That matrix is having some values W1, W2, W3, and W4. Fine. Now imagine a scary mathematical calculation, I call it. Okay, so what I call it? I call it scary mathematical calculation. Fine. You take these word embeddings and you take these another metric data and you pass it through a scary mathematical calculation. What you get in the output is probability of this word being pizza. So for example, pizza is having a probability of 0.8 and dogs is having a probability of 0.2. What you are doing here? You are taking the word matrix, which means word embeddings. You are computing with, you are taking one more metric. You are passing it through a scary mathematical calculation. And in the end, you are getting the probability numbers for word being pizza or dogs. What you see here, right? I'll highlight it in red. What you see here are called parameters of your model. Let that sink in, digest that concept. Whenever somebody is telling that I have X number of parameters in my model, the meaning is all these things that I've highlighted in red color here. All these things sum up together to become X number of parameters. Now let's go back to the newly released meta model page one more time. This is newly released meta model. What is meta saying? The overall data mixture of training consists of 30 trillion tokens. Now you know what is the meaning of tokens. On the top, the meta says 17 billion active parameters, 120 expert, 400 billion total parameters. Forget about active and expert for now. 400 billion total parameters in this model. So now if somebody tells you what is the parameter of your model, you know what is the meaning of the parameter of the model. Parameter of the model is something which is changed or tuned so that I can get the right response most of the time. So these numbers, all these numbers, red circles, right? These can be changed or tuned in such a way that I can get the right answer most of the time. That process is called training the model. Okay, that process is called training the model. Now imagine Meta is claiming 400 billion parameters. So I will write here 400 billion params in this new model Meta is claiming, and Meta is claiming 30 trillion tokens. You can imagine how much of resource intensive this training will be. And that is the reason me and you cannot train a state of the art large language model. Me and you cannot train a language model from the scratch, which is as capable as these big models. But what me and you can do is me and you can understand how these models work, and me and you can take these models, use it for our own purposes. That also we will cover. But first, we started from, if you remember, we started from learning the basics of LLM first of all. And I explained you these two things. These two things. Now we will understand context length also, but it's not that difficult to understand. It is basically the number of tokens the LLM can produce in one shot. Okay, and if you go to new meta model, right, they are saying I can produce. It's a huge number actually. I was so surprised to see that 10 million context length optimized inference. So when you are inference means when you are asking questions to the model, right? 10 million tokens it can produce in, it can process in one shot. That is what it is saying. So not difficult to understand context length. It's an easy concept only. Okay. Now what I want you to be more focus on, if I give you a training data and if I tell you to train a model, right? Forget the very big models. If you understand how these small models are trained, right, you will get a very good picture in your head how things will work. Okay. So what we will need to train a model? We will need some data, correct? We will need, I will do a Python hands-on now. So I'm telling you what we will be doing. We will data to train the model. We will take, fine. From this data, what we should create? We should create tokens, correct? We should create tokens. From these tokens, what we should create? We should create embeddings. Create embeddings, I'll say. Create tokens, create embeddings. From embeddings, what we should do? A normal machine learning process of training model, train model, train model, and then predict. Predict. So I'm going to do this process now in Python. And in this process, our concepts of I want to clarify your concept of parameters very, very clearly with this example. Fine. So let me go to the this one again, and let me paste this because this is important for you to know. So let's go ahead and build the model here. Fine. So what I'm going to do is I'm going to take a sample data first. What I'm going to do is I'm going to take a import some packages basically that will help you to build the model. So I'm importing NumPy, TensorFlow, and since I will be training the model, so sklearn model selection, train test split. Then I need some training data, right? So I will be putting some training data like this. So if you see here, the fluffy cat that was sleeping under the table, the old dog that has been chasing the small bird, lot of things here. Fine. So some training data. You can take any other data as well. What is the first step that we need to do? We need to create a vocab. Vocab means how many unique words are there in my dictionary, in my complete corpus, in my training data basically. What I'm doing here, 4 sentences. Basically, I'm creating a list here that will have all the unique words in my vocab. So my list will look like this. So all the unique words in my vocab will be there in my list. From this list, what I will do is I will create my own tokenization. So I'm doing this from scratch, right? So I will assign one number to all the words and I will create that mapping basically word to number, number to word. So if you see here word to index, I for I in words and index to word. So basically a mapping actually. So if you see word to index, right, you will see that all the words has been assigned a number and this will be reverse index to word. Okay. Index to word has been assigned in a again sequence. So what I want to do here is I want to predict the third word by sending 2 words. So what my intention is, I want to train a model where my model should tell me what is the third word if I give 2 words. Fine. So I will create the words in pairs of 2. So first of all, I will store my vocab length of words, basically how many unique words in my vocab, right, that I'm storing in this variable. So if you see here, vocab size is 72, which means 72 unique words in my sentence, in my training data, basically. Fine. Now, what I will do, as I told you, I will create pairs. The meaning of pairs is from the entire training data, the set of 2 plus 1, 2 plus 1, 2 plus 1, like that. And that is what this for loop is doing. So I will simply show you append is not there, has no object append. X pairs. Okay, I have not created X pairs. Why next? So I need to create this first as a list. and then in the list I can append this, and then I can show you, I can show you how X pairs and Y pairs look like. So X pair is basically combination of two things, okay? And Y pair is basically what is after that. So in the training data, Y next basically, Y next is basically what is after that. So it will be single things. So for example, if you come here, right, 26 and 56, two words, see here what are 26 is the, and 56 is fluffy, okay? So the fluffy is one pair, and what is the prediction for this basically for our training? The fluffy, the word is word number 0, okay? So what is word number 0 in our dictionary basically? Word number 0, cat, okay? So the fluffy cat should be one sentence in our one combination in our line. So you see here the fluffy cat, okay? So this way I'm creating my training and test data, and not test data I have created yet. I have just created these things. So X pairs and Y pairs basically. So I will convert this to ND array because I have to train a model, right? And then I will break it into train and test. So again, that X things and Y things will get broken into two pieces, two sets, not pieces. So till here, whatever I was doing is data preparation only. Now I will do the actual model. In actual model, we need to do the embedding first. And to do that, first I need to define the embedding dimension. Dimension means what is the vector size I want for the embedding. So in this case, I'm saying 5. Okay. So in the previous example, when I was showing you this model, right, the embedding size of large language models are really large. So if you see 3 dots in the end, right, this means it's going beyond this. But in my case, I'm keeping it 5 only. Embedding dimension is 5 in my case. So I want a 5-dimension vector. Fine. Now what I'm going to do is I'm going to initialize a sequential neural network model. So if you see here, right, I will say model is equal to tf.chaos.sequential, and I'm going to start adding layers here. So the first layer in my model will be an embedding layer. Why embedding layer? Because first thing that should happen is embedding, right? The second layer which I want to add here is a flatten layer. Flatten layer, the job of that is the flatten layer will send it to the dense layer. So I'll explain you in a moment. Just let me put all the layers first. Okay. And I will simply close this. So this is my model basically. What this model is doing is, first of all, I am creating an embedding. In this embedding, my vocab size is what? My vocab size is, if you see here, right, I had printed my vocab size. Vocab size is 72, which means 72 unique words. So what I'm saying to my system is, there are 72 unique words in my system. I want you to create a 5-dimensional embedding for all these. That is what this will do. To this layer, I am saying, since I want to send two words together. So in one shot, I want to send 2 words because this is how I have created my data, right? I want to send two words together. So what you should do is you should flatten it in such a way that it can pass to the next layer. Okay. So what it will do is it will flatten it and make it a 10-dimensional vector, or 10 numbers you can think of. And then in the dense layer, I'm giving 8 neurons, and activation function is ReLU. So here I want to recommend you one video. So go to Unfold Data Science on YouTube and search for building one neuron from scratch. Um, Go to Unfold Data Science on YouTube and you can search for Unfold Data Science building one neuron from scratch. Okay. And you will get a video here. Intuition behind neural network is there, and there will be a video called one neuron from scratch. That video coding one neuron from scratch, right? This video you must watch and your concepts will be very, very clear. Okay. On how neural networks work. So here I'm adding a 8 neuron and activation ReLU. And in the last layer, again, I want 72 probabilities because 72 words in my dictionary, right? So I'm saying 72 and activation is softmax. So I will explain you more, but first let me try to show you some things here. I have Once you define your neural network, you need to compile that. Compile that means you tell the model what is your loss function, etc. So I'm saying take this loss, take this optimizer, and take this metric. This is my model, and I can start my training on how many ever iterations I want to do. In this case, I want to do a 20 iteration. So let me train my model. So my model training is starting now. So if you see here, my model has trained 20 epochs or 20 times. And what I can do now is I can predict from this model. So basically I can give two words and model can give me the answer. Model can tell me what is the next word from those two words. But my intention here is to make you understand parameters and how the model is learning. So if I go and do model summary, right? If I go and do model summary, you will see something interesting here. So I'm interested in trainable parameters 1096, how this is coming. I'm interested in this part. Fine. Let's try to understand what network looks like. So first of all, how many words we have in our model? So as we did a count of unique words, right? We got some 72 words. So 72 words will come into picture. For all the 72 words, we asked a 5-dimension embedding. So 3, 4. Word 1 will be a 5 length vector, 5 size vector. Similarly, word 2 and similarly word 72. So how many numbers we want to train here? Basically, we are trying to reduce the trainable parameters, right? So 72 words, and for all these words, 5 numbers. Total number of trainable parameters here will be 72 into 5, which is nothing but 360. And that is what you are able to see here in the embedding layer. So if you go here, right? If you go here, embedding layer, 360 parameters to train, 72 into 5. After that, the next thing what we are doing is we are sending two words together, right? So what will happen is one 5 word embedding plus another 5 word embedding. You can think like this: 1, 2, 3, 4. So this from here to here is one word, and from here to here is second word. Here there is no training happening. It's just reshaping the input. So from here matrix will come like this, vectors will come, and here reshaping will happen. So here there is no training happening. So 0 parameters to train. It's basically flattening. It's basically preparing to send it to next layer. Fine. So 0 parameters here. And what we did next, if you remember the model, or we can see one more time. What we did next is first of all, we created embedding, then we created flatten, then we created a dense layer with 8 neurons. So let's go ahead and try to put 8 neurons here. So 1, 2, 3, 4, 5, 6, 7, and 8. Fine. How many numbers we have here? 10 numbers. How many neurons we have here? 8. So all these 10 things will get connected here with a weight, and that weight could be W1, W2, W3, whatever. But here the weight that we need to train will be 10 into 8. Plus with weights there will be biases also coming. So there will be bias for each of these neuron. First neuron B1, second neuron B2, third neuron B3. So 8 will come from here. Total number of parameters to train here will be how much? it will be 88. And that is what you are able to see here in the model. So when we ask model summary, right, you will see 0 for flatten, and for dense you will see 88. And what about the last layer? Since this is a fully connected neural network, in the last layer we are asking for 72 neurons because we have 72 words in our vocab. And remember, this is a fully connected, meaning all these will be connected to all these. Fine, 72 things. So what will happen here is 72 numbers, 72 weights multiplied with 8 previous layer neurons plus plus 72 biases, because for all the single neurons bias will come. And if you compute this number, right, this will come nothing but 648. If you compute this number, right, this will come nothing but 648. And if you add 360 plus 88 plus 648 plus 0, what you are going to get is 1096. So if you add these four numbers, right, 360 plus 0 plus 88 plus 648, what you are going to get is 1096. And this 1096 is nothing but, yeah, it is 1096. This 1096 is nothing but your trainable parameter of this simple model. So from this example, what I tried to make you understand is how trainable parameters are computed in a neural network. Fine. Now this network is a very simple network. So what I will try to do is I will try to again capture a screenshot, and I will try to put in that file which I can share with you. So let me try to do that. Pictures, screenshots. So anytime you see a model, right, just try to think how the parameters is getting computed by looking at this image. Fine. So you will understand how the parameters is getting computed. So this is, I have pasted this as well meanwhile, where these are the embedding parameters, these are the weight parameters. So you have an idea. So here also some are embedding parameters, some are weight parameters, some are biases. So you will have an idea of that. With that in mind, this model is not a great model. So I will show you what this model is predicting. To show you what this model is predicting, right, we can simply give the word index and we can simply ask to predict next word. If I give, for example, the, and if I give cat as two input words, right, and I'm asking model to predict on this input pair, and I'm asking model to give me the whatever the maximum probability. So let me show you what this model is doing actually. So if you give, so here what I'm doing, I'm giving two words and I want to predict the next word. In the predictions, right, you will see it will give me 72 probabilities. So see here, 72 probabilities is giving. What I need to do is I need to take the highest probability and map it to the corresponding word. So I'm doing np.argmax prediction 0, which means give me the highest probability, that index, and that index I'm mapping it to word. So the word I'm going to get is A. Okay. So I'm getting this word A. So this the prediction is not that great. The reason being this model is a simple model. This model is not a some fancy model. I just try to give you an image of what is happening. Fine. If you have understood these concepts, right, then you have understood solid foundation for what is LLMs. Now let's take a step forward. Now let's take a step forward and try to understand what has been happening so far from 1990. Before this, I will not speak till 2014. So I will write here some important times. Okay, 2017 and 2022. These are the important years in the era of LLM development. So whatever we spoke about, bag of words, one hot encoding, old kind of techniques, or what to wake or static embeddings, right? This is the era for all that thing happening. Fine. And there were memory based models introduced. Memory based models. So what we did now is a simple neural network which is trying to predict the next word. What researchers found is this is not able to do the job. The reason being it is not able to remember the context of in what context what is being said. Okay, so just to give you some example of what is a memory based problems, right? I can say that I can simply say a sentence like the cat the cat the cat ran with a bat of dog which was new. So if you pay attention to these kind of sentences, right? The cat ran with a bat of dog. So at the moment you come here, you say bat of dog means here we are talking about dog's bat, which was new, which means we are talking about bat. So if you pay attention here, the word bat and which are related. So when the language model is learning, right, it should understand that when it is reaching the word which, the which is being spoken in the context of bat. So the word which is being spoken in the context of bat. And this intelligence, researchers have tried to put into the model through many techniques. And one such technique is known as memory based model. So what researchers did is they thought, let me start putting when the model is trying to understand or predict the next token, let me try to feed back the previous token information as well. So when I say previous token, so I'm not talking about when the model is trying to predict which, I should give the model information about dog, of, bat, with everything that is before this. These kind of models is called memory based model, where model will remember the information of previous state. So for example, if you call this current state, this word which, this dog will be the previous state, this will be the kind of one previous state, and like that. These memory based models were primarily built using sec to sec or sequence to sequence kind of architecture. So what is sequence to sequence architecture is basically you can think of there will be an encoder. Encoder is one kind of neural network. There will be a decoder. Decoder is another kind of network or learning. And if we give a sequence to sequence problem, for example, language translation problem. So here if I say, I am good, this is an English sentence, then encoder will understand the context of this entire sentence and it will generate something known as context. So this will be called as context. This context will go into the decoder, and decoder, let's say, will try to convert this to a Hindi sentence. For example, मैं अच्छा, this is a Hindi word basically, Hindi line, मैं अच्छा हूँ. So in encoder decoder architecture, what this problem is called a sec to sec problem because it is solving a sequence. So this is a sequence of words, right? And this is again a sequence of words. So it is solving a sec to sec problem. And this kind of architecture is called encoder decoder kind of architecture. So how it works is encoder will encode, generate a context of that sentence, and decoder will decode, and in this the learning will happen. There are two famous algorithms that I want you to know. One is called recurrent neural network and another is called LSTM, long short term memory. In recurrent neural network, what happens is the memory of the previous state is sent to the network to understand the context. In long short term memory, the memory is sent again, but slightly different than RNN and LSTM. But remember, both of these are working on remembering the information of the previous state, and hence these has bottlenecks. So suppose this is the sentence, right? If the sentence becomes really big, right, it's very difficult to feed that into the model again and again and optimize the model parameters. So all these things keep happening till the year 2014. In 2014, a new concept came into the market. The concept was known as attention. The concept's name is attention. And what attention tells you to do is, attention tells you, hey, you no need to remember all the information. If you are remembering, remember it. But my funda is, I will just pay attention to all the words of the sentence with respect to all other words of the sentence. So, for example, if I am writing here, I am good, I will write here, I am good. And what attention's philosophy is, attention tells you that you have to pay attention or pay focus to some words in a sentence when you are talking about one word. For example, when you talk about I, then you need to pay attention to I with a score of 0.9. When you are talking of M, then you need to pay attention to I 0.6. When you are talking about word good, then you need to pay attention to this 0.2. Similarly, when you are talking to I, you get the idea, right? So basically, when you are talking about good, how much attention you want to pay to the word aim? So maybe 0.7 attention you want to pay. Some number, some scoring. We will go into detail, don't worry. What attention told is, you guys are facing difficulty in remembering the information of the previous state in a longer sentences. I come up with this solution where you need to just remember the attention, where to pay attention, and that will do a lot of good things for you. So initially before 2017, right, in between 2014 to 17, lot of model came where in encoder decoder architecture, they also added one kind of attention. So you can think of this as a feedback, and this is kind of attention feedback. So when somebody is generating the Hindi text, right, when somebody is trying to generate this word, right, it will try to get attention score into picture and try to see where to pay attention to. Fine. This is a concept of attention. At this juncture, I want to give you some learning materials which will make your life easy. Let's go to YouTube. First of all, go ahead and search for Unfold Data Science coding one neuron from scratch. I know last time I was showing, it was not showing due to some problem. Coding one neuron from scratch, you search, you watch this video, you will understand how a simple neural network works. Fine. Then you go and search for Unfold Data Science RNN. You will understand what is an RNN architecture, how it works, and what are the problems of RNN. Then you see this encoder decoder sec to sec architecture model. You will understand what is encoder decoder sec to sec architecture, how it works, and what are the problems with this. Then you can go here and search for Unfold Data Science LSTM. You will understand how LSTM works, and there is a LSTM next word prediction video also that you can see to understand how to implement a LSTM model. If you watch these things, right, you will get a very good idea of how these models work, what has been development so far, and how it is working. All these videos are together in this playlist. You can search Unfold Data Science Generative AI for Beginners. In this playlist, you will see all these videos, and in all these playlists, all these videos you will find. But there is one video which I do not want you to miss, and that is very important for the next lecture in this series. And that video is on attention mechanism. So if you go and search Unfold Data Science attention mechanism, right, you are going to get a 35 minutes video, and you can read the comments on this playlist, or if you open this video, you can read that as well. Here I have explained you how attention is computed. This is a must to watch video before you come to understand the next concept of this playlist. If one video you have to watch, that is this video. If you want to understand more concepts around LLM, LSTM, RNN, etc., you watch all these videos. But attention video you must watch. Now let's come back to our discussion. There were attention discussions till 2014, but in 2017, the very famous research paper came by Google, and the name of this paper is Attention is All You Need. Okay, attention is all you need. This is one thing that I always keep on my desktop, this paper, because this paper is the reason you are having ChatGPT application in your mobile phone. There is this paper that is the reason of all the advancement in the field of LLM. To understand this, attention is all you need basically tells you the transformer architecture. Okay, so this paper explains what is the transformer architecture and how it works and how they have built the first transformer architecture basically. And this has changed the entire landscape of large language models. So, as I told you in the beginning, whatever steps we are taking the steps in learning this transformer architecture. And now, after this, in 2022, ChatGPT was released, and rest is the history. You know what has happened after that, right? So, the foundational concepts you need to be very, very careful and you need to be very, very solid with. So, today we covered what are tokens, what are embeddings, what are context length or context length of the model basically, and most important we understood what is the meaning of model parameters. We also understood how a basic language model can be trained. We also understood what has been happening in the field so far, and we understood how attention and transformer mechanism has become so important. What you need to do is you need to watch attention video. That is a must. Watch attention video. If you watch that video, you will understand how these numbers are getting computed. Once you have these numbers, right, and once you have the embeddings, and once you know how a neural network work, two things I've already given you: how embedding works, how neural network work. If you understand how attention works, right, then you are ready to understand the transformer architecture. Once you understand transformer architecture, then you are ready to play around with large language models, which is what we will do in the next lectures. There are some more topics apart from attention that also we will cover one by one. But till here, go ahead and watch that attention video and other videos also if you are interested. So your comments and likes are my motivation, guys. If I see less comments, I get demotivated. Please give me more comments. Please let me know how I am doing, and I'll come up with more interesting videos. See you all soon. Take care.